In this lesson, we introduce arithmetic in different bases. We will see that addition, subtraction, and multiplication work in the same structured way across different number systems, even when the symbols and carrying rules change. Before looking at calculations, we need 4 basic arithmetic properties. These properties explain why arithmetic remains predictable. They are the reason we can rearrange, group, and combine quantities without changing what those quantities mean. The first property is called closure. Closure means that when we perform an operation on 2 numbers in the same number system, the result is also a number in that number system. For example, if we add 2 binary numbers, the answer is still a binary number. If we add 2 base 8 numbers, the answer is still a base 8 number. So if A and C are numbers written in base k, and k is a base of the number system, then A plus C will also be representable in k. This means that we do not leave the number system just by doing arithmetic. We can start with numbers in a base, perform an operation, and still describe the answer using symbols from that same base system. The second property is called associativity. Associativity tells us that the grouping of numbers does not change the result. For addition, this means A plus C plus D is equal to A plus C plus D. Here, A, C, and D are numbers, and the brackets show which operation is performed first. The answer stays the same, even if the grouping changes. This allows us to break a calculation into smaller parts. Whether we add the first 2 numbers first or the last 2 numbers first, the final quantity is unchanged. The third property is called commutativity. Commutativity tells us that the order of the numbers does not change the result. For addition, it means A plus C is equal to C plus A. For multiplication, this means A times C is equal to C times A. So we can swap the order of the numbers without changing the answer. This really means that quantities do not depend on the order in which we name them. 3 groups of 5 objects gives the same total as 5 groups of 3 objects. The structure of the calculation changes, but the quantity represented by them stays the same. The fourth property is called distributivity. Distributivity connects multiplication and addition. It tells us that multiplying a number by a sum is the same as multiplying each part separately and then adding the result. So we have A multiplied by C plus D is equals to A times C plus A times D. This explains why long multiplication works. When we multiply a number with many digits, we are really splitting that number into place value parts, multiplying each part separately and then adding the partial results. These properties hold in different bases because the base changes how numbers are represented, but it does not change the underlying structure of the arithmetic. Now let's look at addition. Suppose we want to add the binary numbers 1, 1, 0, 1 and 1, 0, 1, 1. The small 2 at the bottom right of these numbers tell us that these 2 numbers are written in base 2. In base 2, we only have 2 digits, 0 and 1. Firstly, we align the numbers on the right, just as like we would in base 10 addition. Then, we start from the rightmost column. First, 1 plus 1 is equal to 1, 0. Now we see a carry value of 1. In base 2, we cannot write the quantity 2 using a single digit. So we write 0 in the current position and carry 1 into the next position. That carried 1 means one group of 2. In the next column, we now have 1 plus 0 plus 1. This is 1, 0 in binary again. So we write down 0 and carry 1. In the next column, we have 1 plus 1 plus 0. Again, this gives us 1, 0. So we write down 0 and carry the 1. In the leftmost column, we have 1 plus 1 plus 1. In binary, this is 1, 1. So we write down both digits in the front. The final answer is 1, 1, 0, 0, 0 in base 2. The process is the same as ordinary addition. The only thing that changes is when we carry in base 10, we carry when the column reaches 10. However, in base 2, we carry when a column reaches 2. In any base, carrying means the current column has reached one full group of the base, so that group moves to the next position. Let's now look at subtraction in a different base. Suppose we want to subtract 1, 4, 6, 7 in base 8 from 5, 3, 2, 4, also a base 8 number. The small 8 at the bottom tells us that these two numbers are written in base 8. In base 8, the available digits are 0, 1, 2, 3, 4, 5, 6, and 7. We align the numbers to the right as we did before. Then we start from the rightmost column and firstly calculate what is 4 minus 7. We cannot subtract 7 from 4, so we borrow from the column to the left. Borrowing is the reverse of carrying. When we borrow 1 from the next position, we are breaking one larger group into smaller groups in the current position. In base 8, 1 unit from the next position becomes 8 units in the current position. So the 4 becomes 4 plus 1, 0 is equal to 1, 4. Then 1, 4 minus 7 is 5. So the rightmost digit of the answer is 5. The next column has been reduced because we borrowed from it. So the 2 becomes a 1. Now we need to calculate 1 minus 6. Again, we borrow from the column to the left. Borrowing 1 gives us 8 more units. So we have 1 plus 1, 0 is equal to 1, 1. Then 1, 1 minus 6 is equal to 3. So the next digit is 3. Now the 3 in the next column has been reduced to 2. We calculate 2 minus 4. Again, we need to borrow. The 2 becomes 2 plus 8 is equal to 1, 2. Then 1, 2 minus 4 is equal to 6. So the next digit is 6. Finally, the 5 on the left has been reduced to 4. So we calculate 4 minus 1 is equal to 3. The final answer is 3, 6, 3, 5 in base 8. So 5, 3, 2, 4 minus 1, 4, 6, 7 is equal to 3, 6, 3, 5 in base 8. The method is essentially the same as subtraction in base 10. The only difference is that borrowing gives us 8 units instead of 10, because we are working in base 8. So subtraction also follows the structure of the base. The base tells us how many smaller units one borrowed group becomes. Now let's look at multiplication. Suppose we want to multiply the binary numbers 1101 and 101. In binary multiplication, each digit of the multiplier is either 0 or 1. This makes multiplication very simple. Multiplying by 0 gives us 0. However, multiplying by 1 gives us the original number. We align the numbers on the right and start with the rightmost digit of the multiplier. The rightmost digit is 1. So we write down the multiplicand 1101. The next digit of the multiplier is 0. So the next partial product is 0. Because this digit is one position to the left, the partial product is shifted one place to the left. So we get 0, 0, 0, 0. The next digit of the multiplier is 1. So we write down the multiplicand again. Because this digit is two positions to the left, we shift the partial product two places to the left. So the partial products are 1101, 0000, 1101. Now we add these partial products. 1101 plus 00000 plus 110100 is equals to 1000001. So 1101 multiplied by 101 is equal to 1000001. This is the same idea as long multiplication in base 10. Each digit of the multiplier creates one partial product. Each partial product is shifted according to its position. Then the partial products are added together. The reason why each partial product is shifted is because each digit in the multiplier is not just a digit by itself. Instead, its position tells us what size group it represents. A 1 in the rightmost position means one copy of the number. A 1, one position to the left, means one group of two copies. A 1, two positions to the left, means one group of four copies. So multiplication is repeated addition, organized by place values. The reason base arithmetic works is that the base changes the size of the groups we are counting, but not the logic of the operations. In base 10, carrying and borrowing happen in groups of 10. In base 2, they happen in groups of 2. In base 8, they happen in groups of 8. Addition combines quantities, subtraction removes quantities, multiplication repeats quantities. The symbols may look different across different bases, and the carrying or borrowing may happen at different points in time, but the arithmetic structure stays the same. That is why the same operations can be performed consistently in any base.